Okay, we are working on this example of mass moment of inertia. So you see this plate is made of a square. So that's why I took the mass moment of inertia of a thin plate and 4 circular disks. We want the mass moment of inertia about O, so about this axis there. Maybe we can think first about finding the moment about each center of the disk and move it to O. But you can see right away that it will be a nightmare. So a good strategy there, a good strategy there will be to try to just remove this one. Here we go. A good strategy will be to move the mass moment inertia at the center of the plate, because that's the centroid of the plate, and after move it to O. So that's what we will do. Okay. Clean that a little bit. So let's do, I will call this G. Okay, we are looking to find the mass moment of inertia about O, and we have the mass moment of inertia of each little circle. So for the plate, mass moment of inertia for the plate at G, okay? For the plate at G, that will just be the ZZ equal 112. So that will be, I will call I plate at G, okay? That will be 112 of the mass of the plate. So the mass of the plate, we will find it after, time the 2 dimensions, that is the 400 millimeters, so that's 0.4 square plus 0.4 square. Let's get the mass of the plate. So we have the density, so the mass of the plate will be 20 kilograms times the area, that is 0.4 times 0.4. Oops. How much is that? Let me find it at the same time. I must move that. That will be, try to get all my windows open, but sometimes this is 3.2 kilogram. And for the disk, I know it will be a negative mass, but let's find the mass of each disk right now. So the diameter is 50 millimeters. So that will be pi times 50 divided by 2 to have the radius square times the density. So the mass of each disk is, let me just make a modification. That's not 50 divided by 2. That will be, oh no, that will be 0.05. 0.05 divided by 2 square times 20. So that gives me 0.039 kilograms. Okay, so we have the mass of the plate and the mass of the disk. So the IP at G, the center of the plate, is equal to 112 times 3.2 times the 0.4 square plus 0.4 square. This value is IPG equals 0.085. That's a kilogram meter square. Okay, remember to keep your exact number in your calculator, always. So that's the MMI at the plate at G. Now the MMI of the disk at G. Okay, first I will find for one disk. So one disk, that will be the mass moment of inertia about the axis Z, so this one. So that will be 1/2 of mr squared. So that will be I disk D at G will be 1 divided by 2 mr squared plus the distance squared times the mass of the disk. That's for the disk, and the distance is 1.5. So IdG is equal to 1/2 of the mass, that is 0.039. The radius is 0.025. So the diameter, let's write it there. The diameter is 50 millimeter, so it's 0.05 meter So the radius is 0.025 meter. That's a 5. Okay. Square plus the distance. The distance is provided on the figure, that this 150 millimeter. The vertical or horizontal distance, they are always the same. So that's 0.15 square time again the mass, that is 0.039. So the ID of the disk is, that's very small, so that's 0.000896, and that's kilogram time meter square. So at the end, the I at G will be the IP at G minus 4 times IDG. Okay, so the IG will be 0.085 minus 4 times 0.000896. So that gives us an I at G that is equal to 0.0, and that's exact number, I think, 8175, and that's kilogram time meter square. Are we done? Not exactly, because what we want is the IO. Let's look at this figure. Okay, we want the IO there at O. So we have to move the mass moment inertia from 0 to G. And what we can do that? We can do that only because this G is the center of gravity of the plate, the total shape. If that was not the center of gravity, let's, for example, if we don't have one of the circle there, the center of gravity will be a little bit higher, and we will not be able to do that. That's only because we can, the G is the center of gravity of the plate. So we need to find this distance. Let's call this distance D. How do we find this distance D? We have, this one is 400, and we try to find this distance D. So this is the different options, but this is a 45 degrees. So we can use sine of 45 degrees equal D divided by 400. So we get D equal 400 times sine 45. And that's, you know, the 400 times square root of 2 divided by 2. So we can write that D equal 200 times square root of 2 in millimeter. Okay, so we can use that. Just checking my numbers. So let's now move to IO. Okay, oops. We have IO equal IG plus D squared times the mass of the entire system. So that will be IO equal 0.08175 plus the distance that we found, that is 0.2 square root of 2. Don't forget to have everything in meter. Oops. 0.2 square root of 2 square times the mass of the plate. That will be the mass of the plate minus 4 times the mass of the disk that we found there. So that will be, let me write one more step. IO equals 0.08175 plus 0.2 times square root of 2. That will be just 2 with the square. But let's write everything time 3.2 minus 4 times 0.039. So we have at the end IO equal to 0.325, and there's some numbers after that, kilogram time meter square. Let's see if we get something that looks correct if we look at KO. So the KO is the square root of IO divided by the mass. So we should have KO equal the square root of IO 0.325 divided by the mass. So the mass was the 3.2 minus 4 times 0.039. Okay, forget parentheses there. That's a 9. How much is KO? We hope to have something around maybe 200, 300, between 200 and 300 in millimeters, so 0.2, 0.3. That will give us 0.327, and that's meter. So KO equal 327 millimeter. That makes sense. Like 300, you see, like this, we found that this distance is 200 square roots of 2. So like about almost 300. So the distance D is almost 300. So it's a little bit more than 300. That makes sense. It's inside the plate, at least. So in that problem, what we need to look for, we need to look for an intermediate center that will help us to find the moment of inertia about O. If we begin right away with O, so O was there, if we begin right away with O, that will be very challenging to find all the distance. So what we did, instead of using all those distance, we use the point G in the middle, and we move all the circles first. Oops. We move all the circles first at the center. And we found the moment of inertia about G, an axis that is perpendicular to my screen, going through the point G, and after that we move it to O, using that final distance D. Okay. Be careful of your units, because of the units are given in millimeter, but you want the value in meter. You don't have to change your unit. If you want to keep millimeter from the beginning to the end, I personally think it's a little bit easier than changing from meter and having very small number, but it's completely up to you. And be careful of which axis you are using from your formula sheets. So in that case, that was Z and that was Z. And that's it for this example. See you later. Bye-bye.